And we're live.
My internet students are going to wonder who the heck that mystery voice is, but that's okay. So here's what I wrote down. You're going to want a calculator handy, I think. If you don't have one, you may want to borrow one from up here and just leave me some collateral. I'll try and make the numbers sometimes work out nice, but sometimes the numbers get messy and decimal-y thingies. Section 9.1, we're talking about acceleration. So we've already examined what we called uniform motion. Uniform motion was what? Hey, that was an object traveling with, so an object traveling with uniform motion means it's going at a constant speed or a constant velocity. Here's what it really means. It has equal displacements, I forgot to put the word equal, in equal time intervals. If you're traveling the same distance in the same amount of time, your speed's not changing. You're in uniform motion, you're not accelerating. If you're speeding up or slowing down, if your speeds are different between two time intervals, that means you'll cover a different amount of space. Really, uniform motion equals constant velocity. That's the way I think of uniform motion. But because you're going at a constant velocity, then, Jake, it means that every second you're traveling the same distance. If you travel twice as far in a different second, your speed must have changed. You're no longer uniform motion. And then I wrote here, hey, not all objects exhibit uniform motion. We looked at a few examples last day, free fall being a great example. So it's important to be able to analyze situations where the motion is not uniform. An object traveling with, fancy word, non-uniform motion will have what? Well, first of all, it will have different displacements during equal time intervals. So, Kenzie, if in the first second it traveled 20 meters, if in the second second it travels 40 meters, that's not uniform motion. It's sped up. If in the first second it traveled 20 meters and in the second second it traveled 10 meters, that's not uniform motion. Oh, and it slowed down. Or if you're traveling the same distance, it will take different, Mr. Dewick, learn to spell, good gosh. Different times to travel equal displacements. So Hayden, if you run around the track behind us in 90 seconds and then you run another lap of the track behind us in 180 seconds, you ran the same displacement, same track, different times. One of those speeds was not like the other. One of those speeds just doesn't belong. Little Sesame Street for you there. Really what this means is if you really want to get high tech, and we look at this in Physics 11 and Physics 12, you can have a continuously changing, what's the letter V with a vector symbol above it, an abbreviation for? You're right, loud. Yeah, velocity. What if I left off the vector symbol? Speed. What is acceleration? Acceleration is how fast your velocity is changing. We're not going to write that as a definition. I'm going to give you a bit more of a formal definition. But Ty, if you know an object's acceleration, what that's really telling you is how fast it's speeding up or slowing down. Whenever we say how fast in science, what we really mean is the rate of change. So what we're going to write is this. Acceleration is the rate of change of velocity. So I'm going to give you an English definition. I'm going to give you the provincial exam formula sheet. And then I'm going to give you the one that I, in Physics 11, always use, because I would much rather get the most functional form. Amy, you with me? One more time and I'll move, you guys. Thank you. So, what would be a good letter to use for acceleration? Sure. Acceleration. It is a vector. Now, I'm going to get fussy. Oscar, what we're technically always going to be finding is the average acceleration, but in Physics, Science 10, and in Physics 11, and to be honest, in Physics 12, we're always going to deal with a constant acceleration, which means the average and the acceleration is going to be the same. We're not going to change. To deal with a changing acceleration, you really need calculus. It's defined as what does the delta stand for, the triangle? What's that an abbreviation for? Okay, this is really change in velocity divided by change in time. And folks, this you need to know, so it bears rewriting down. Over here on the right, delta equals change in, and when you see that delta, you think change in, but what do we really mean? So when you see delta V, what you're really looking for is a velocity later, final, and the velocity before, at the beginning, at the start, initial. And then time is the weird one. Time is always a change in, because you're always starting and stopping a stopwatch. Almost always, Jacob, our change in time starts at 0. Not always, though, so we'll leave it there. I prefer this. Because what's change in? Final minus initial. Amy, this is how I teach it in Physics 11. But on the provincial exam, what you're going to get is this bad boy here in blue. Although, can you see, Miller, really when they write this, they are giving you this one because change in anything is final minus initial? My argument is, why not just give you that one? But I'm not in charge. What are the units? Before you turn the page, what are the units? Well, the units are meters per second, because it's velocity divided by time. It's meters per second. Except, do you remember what we said a couple of classes ago? How do we write that instead? We write it as meters per second squared, because you got two S's on the bottom. It's easier to write that. There are other ways to measure acceleration. Meters per second squared is by far the most common. Turn the page now. This, good gosh, Mr. Duick, my spelling is going out to lunch. Acceleration can be due to a, what's that a symbol for? Change in speed. Or it can be due to a change in direction, or both. Both is pretty tough. In fact, both really is physics 12. You need some vector math and some trig. Okay. So, two objects with the same change in velocity can have different accelerations. Suppose Justine and Ty are having a go-kart race. And Justine starts out at 0, and so does Ty. And they both give their car gas, but Justine is much more aggressive than Ty. Justine floors it. She reaches a final speed of 100 kilometers per hour in 15 seconds. Ty reaches a final speed also of 100 kilometers per hour, but he takes 30 seconds. Your change in velocity was the same, because did you hear what I said? Your initial was 0, your final was 100. You both had the same change in velocity, but since you took way longer to get there, your acceleration is going to be slower. So, same change in velocity can have a different acceleration. Why? Because acceleration describes the amount of time in which the change occurs. So we have here a little jalopy, an old car, and a dragster. You know what? Let's call this dragster J for Justine, and let's call this little piece of car T for Ty. Suppose each vehicle above had a race to see which vehicle could reach 100 kilometers per hour first. First of all, what's the change in velocity for each vehicle? Well, what they're asking is, what's that? What's change in anything? Now, you may already know the answer to this, but I'm going to walk you through the math so that when the numbers aren't that easy, you can crunch the numbers still. It's going to be, Justine, you are correct, final minus initial. What's the final velocity of each of these cars? 100 kilometers per hour minus. Trick question, what's the initial velocity of each of these cars if they're starting at rest? 0? So the change in velocity is, or the change in speed, because I haven't given you a direction, is 100 kilometers per hour. Now, if we want to get this in meters per second, we'll do our conversion later. But for now, do you agree with me, Ty? You both undergo the same delta V, the same change in velocity. Yeah. Does this mean they have the same acceleration? Why? You're right. Why don't they have the same, or why not don't they have the same acceleration? There's a shorter way to write that. Yeah, the change in time, the delta t, not the same. Justine obviously took way less time, assuming you guys both floored it. Yeah, keep your eye on Justine. I know. Okay. Turn the page. So since we just turned the page, let's write our acceleration equation right here. When would acceleration equal 0? Or, can you tell me another way that you might not be at rest, but your acceleration would still be 0? Oh. At a constant speed. Real world example at rest. Sitting in a chair, all of you right now have no acceleration. If we ignore the rotation of the Earth, which we're going to.
Or else there would be no real world example, and we never ignored that, would it?
Well, this is, so Dane said, well, there would be no real world example if we ignore it. This is where Albert Einstein, one of the reasons it's called the Theory of Relativity, what he started to say is, well, none of us are sitting still. Maybe nowhere in space is sitting still. Maybe it's all relative. What you think of as sitting still is correct. You are sitting still mathematically if we make you the center of the universe. But mathematically, I can make me the center of the universe, in which case I'm sitting still and all of you guys are rotating or moving around me, and that's perfectly acceptable. And the laws of physics hold everywhere. That was the first thought experiment that he started thinking about, where then he started asking, what is acceleration? And he also clued in that acceleration and gravity are very related. Take physics 11 or 12. Can you give me an example of a constant speed? Sure. But you know what? Let's add walking at steady pace. Or jogging. Most of you jog at a constant speed. Okay. Basically, a marathon is a good example. If we ignore the start and if we ignore maybe the final couple of miles when they suddenly kick it up a notch, in the middle there, they're going at a pretty constant speed. There's not much acceleration.
Like if they're on a treadmill or something.
Treadmill? Yep. Acceleration would be positive if what? Sure. Real world example. Pressing the gas pedal. Of a car. More obscure one. Well, we'll come back to it. We have room to add something underneath there. There is a more obscure one. Let's go to the next box. Acceleration would be negative if speeding up backwards. Reverse, then press gas pedal. Can you have a negative acceleration even if your car is traveling forwards?
Slowing down.
Ah! Oop, that's terrible. Slowing down. Nice. Hitting the brakes when you're moving forward. I had to add that in brackets because what if you were in reverse traveling backwards? Do you hit the brakes then to come to a stop? Yeah. If you did that, you're traveling backwards, you're in reverse, and you hit the brakes, what direction is your acceleration then? Ah, here was the obscure example. Going backwards, but slowing down. Right? It must be. I mean, if hitting the brakes when I'm going forwards, Kenzie, is a negative acceleration, then hitting the brakes when I'm already traveling backwards must be a positive acceleration because I'm slowing down in the opposite direction. Another word for opposite is positive or negative. Turn the page. So you ready? And then I wrote a big blank, and then in brackets I have room for a symbol. I'm going to try writing the symbol first, and if you know what the symbol means, you can fill in the blank. Delta V. Oh, change in velocity? Occurs when the speed of an object changes or its direction changes. Because remember, acceleration is a vector, and all vectors have both magnitude and direction. So since acceleration is change in velocity over time, you can change your velocity two ways. Velocity is a vector. You can change the magnitude, that's the speed, or the direction. And one more time, how can I calculate a change in velocity? What does change in anything mean? Final minus initial. Again, Justine, they won't write final minus initial on the green on your formula sheet on the provincial, but whenever you see that delta, final minus initial. I worry you're going to see the triangle and freeze up and forget when really it's, hey, find the final thing minus the initial thing, go to your calculator. Okay? Now, here we figured out the direction of the acceleration kind of intuitively. If you want a mathematical way to do this, if the change in velocity, the final minus initial, is the same sign, plus or minus, as the initial velocity, the speed is increasing. The magnitude of the speed is getting bigger. We say you're speeding up. Now, you won't have to worry about this too often except for in really weird examples. It's usually, Amber, pretty obvious whether you're speeding up or slowing down. But if you're not sure, ask yourself, if I go final minus initial, if I get a negative answer and my initial velocity was negative, well, my change in velocity is in the same direction as my initial velocity. I'm going to be going faster and faster and faster and faster and faster in the negative direction. If the change in velocity is the opposite sign, opposite plus or minus, of the initial, speed is decreasing. What about if the change in velocity, if you go final minus initial and you get 0? What does that mean? Miller. Object has, we can say, one of two things. Constant speed or, I don't know which, because if you're stopped, your final and your initial are going to be 0 anyways, Jessica. We call that the trivial or obvious example. Or you could be going at a constant speed. Oh, the fancy word for that was, you may recall, uniform motion. So I wrote down here, note, an object can be at rest and have uniform motion. Its motion is really uniform. It's not going anywhere. It's just staying where it is, which is about as uniform, as constant as you can get. So far, so good. Lots of conceptual stuff here. We haven't actually started crunching any numbers yet. We'll get there. Positive and negative acceleration. The acceleration direction is the same as the direction of the, if I write delta V, what does that really mean? Change of velocity. We're getting used to this. I'm trying to encourage you to use the symbols because it's a good way to memorize them, and you need to know them for the test and for the provincial, Justine. So if your change in velocity is negative, then you're accelerating down, or or west, or left, or whatever you have described in your reference frame as negative. We have a fancy schmancy word, acceleration that is opposite the direction of motion is sometimes called deceleration. You may have heard the term. In fact, that's probably a term that you're most familiar with when you hit the brakes. You guys go for your driver's license tests this year during your grade 10 or 11 year, right?
Yeah.
So probably in your little manual, it'll talk about when you hit the brakes, you decelerate. Okay. This is really a negative acceleration. So you ready? Let's look at some examples here, little pictures. Okay. Psst. A car speeding up in the forward direction, and the velocity is in the forward direction too. So let's designate the forward direction as positive plus. Okay. The change in velocity, if you're speeding up, do you think your change in velocity is positive or negative? And if you're not sure, just make up some numbers. How about my initial is 5, my final is 10. What's changed in anything? Final minus initial. What's 10 take away 5?
5.
Positive, you say? Is positive. Therefore, the acceleration is positive. Why? Because your initial velocity was positive, and your change in velocity is positive. They're in the same direction. That means you're accelerating in the positive direction. Justine has been clever enough to turn the page. What if we have a car that's traveling forwards but it's slowing down, still traveling forwards. Its acceleration is to the left when its velocity is to the right. What direction do you think the acceleration is, positive or negative? Let's see if we can convince ourselves. So if we designate forward as positive, the change in velocity is negative. And I'll convince you. Let's make, and I always make up nice numbers, Amber, when I'm trying to convince myself. Let's have the initial velocity be 10. Let's have the final velocity be 5, because it is slowing down, yes? If you go change in anything, that would be 5 minus 10. You get a negative change in velocity, yes? What direction is the change in velocity, negative or positive, Amber? What direction is the initial velocity, negative or positive? Are they in the same direction? Nope. Acceleration is negative. Now, you guys all saw that one, but if it's a more confusing example, Justine, I've given you a way you can find your way there. Remember what I said, Sarah? I said if your delta V, your change in velocity, is opposite from your initial velocity, it's a negative acceleration. You're slowing down. Okay. What if we have a car speeding up in the backward direction? So now I've given you some initials and some finals, actual numbers. If we designate backwards as negative, which makes sense to me, what direction is the change? What's the sign of the change in velocity, negative or positive? Let's find out. I know that change in anything is equal to what? Final minus initial. What's our final velocity? Look at the little picture. I gave you numbers this time. Sorry? What's the final velocity? Look at the picture. Negative 4 minus. What's the initial velocity? Negative 1. Negative 4 minus minus 1 is negative 3. Sorry, did I go... Yeah, this works. I'm looking at the wrong example here. So, pardon me? There is a minus minus right there, so a minus minus is a plus. It's really negative 4 plus 1, which is still negative 3. Yes, yes? We would say this. Oh, change colors, Mr. Dewick. This means that the acceleration is negative even though the car is increasing its speed. It is speeding up, but it's speeding up in which direction? In the negative direction. So the change in velocity is in the negative direction. So its acceleration is negative. Remember, positive and negative refer to directions. Couple more and I'm done. Okay, what about if you're going backwards, but instead of speeding up, you're slowing down? Which way do you think the acceleration is? So if you're in reverse, oh, we talked about this. If you're in reverse, but you're slowing down by hitting the brakes, we said we think that's positive. Let's see, Dylan, if we can convince ourselves, if we can prove it. Here's our final one. If we designate the backward direction as negative, then the change in velocity is, Miller says positive. Convince me. I can. I know that change in anything is equal to final minus initial. Let's make up an initial velocity of negative 10 meters per second. In front of it, there would be a minus, because change in anything is final minus initial. If you're slowing down in the backwards direction, what would be a good number to make up for our final velocity? Brendan said negative 20. Is that slowing down in the backwards direction, or is that speeding up in the backwards direction if our initial is... I think that's speeding up. You know what? I think I would say, how about... Right? By the way, the tricky part about this, Brendan, is keeping the signs and the positive and negatives. That's why I'm spending so much time on this. I'm trying to give you a intuitive but also mathematical way to get there. Because Miller already said, I'm pretty sure the acceleration is positive. He's correct. But Laura, we can prove it, because what's a minus minus in the middle there the same as? Yeah, negative 5 plus 10 gives you a change in velocity of positive 5. So you ready? The change in velocity is positive. This means that the acceleration is positive, even though the car is slowing down. Now pause for 1 second. Stay on this page, because this is the tricky one to wrap your brain around. You all stay here. Remember what I said way back when. We said this. If the change in velocity, that delta V, Nicole, has the same sign as your VI, speed is increasing. Here's our final example. Our delta V was positive, but what was the sign on our VI that we made up? Negative. That means the speed is decreasing. That matches what I said? Yep. Now, how can I get the direction of the acceleration? The direction of the acceleration comes from whether this is positive or negative. It comes from your final minus initial. Because remember, positive and negative refer to direction. Direction. So I have some practice for you. Take a look at this. Let me walk you through the basics here. Again, the answers are always attached. I think the answers are right. We've found a couple of mistakes as we go through this. So my usual deal, if you're sure you found a mistake in the answer key, let me know and you get a candy. First one, some vocabulary. So it says, use the terms in the vocabulary box to fill in the blanks. You may use each term only once. I'll let you try and figure out what goes in here. A lot of it will be right from our notes or very, very similar. Take a look at the back of page 1. So here are situations where you're attempting to describe whether you have a positive acceleration, a negative acceleration, or zero acceleration. Miller, I think your method is the best. You were doing a lot of these just by scratching your brain and intuitively kind of... that to me is the best way to figure out whether it's positive or negative. I did try and walk you through if you're not sure, if it's a really tricky one, make up a reasonable initial that matches their condition, make up a reasonable final that matches their condition, and go final minus initial. If it's negative, that's a negative acceleration. If it's positive, it's a positive acceleration. What about slowing down or speeding up? If your delta V, your change in velocity, matches the same sign as your VI, then you're speeding up. You may be speeding up in the negative direction, but you're speeding up. Otherwise, you're slowing down. Number 2, In each example below, identify whether the object or person has positive acceleration, negative acceleration, or no acceleration. And then we have some some multiple choice. I'll let you figure those out as well. Folks, short lesson, you got the remainder of class to work on those. Go right ahead.